All right. Thank you very much, Bill. So for some of you, this is the second talk that you are probably attending. I've given a talk about overview of structured streaming earlier this day. So for those who are, for this is the second talk, welcome back. You guys are really brave and patient. For those who haven't seen my previous talk, that was a more general overview. So I've kept a very brief overview of structured streaming in this talk, so there is some overlap, but if there are questions that, basic questions that aren't clear in this talk, I highly encourage you to take a look at my previous talk when the slides get published and the video gets published. So here I'm going to dive deep, quite fast. Okay, so a brief overview. What structured streaming is a stream processing engine on top of the Spark SQL engine, and it's designed to be fast, scalable, fault-tolerant. It has rich, unified, high-level APIs using the DataFrame and dataset APIs that you probably already heard about in other presentations in the summit. And it's designed to deal with, simplify processing complex data and complex workloads, combining batch, streaming, interactive, machine learning, all of them together. And there's a rich ecosystem of data sources that integrate with many storage systems, again, to ease and simplify the process of combining various different storage systems together. So, and the key idea is that you as an end user should not have to reason about streaming, should not have to reason about complexities of late data, how do you deal with failures, etc. All of them should be seamlessly taken care of by the engine. So you should have to write only simple streaming, simple queries in batch-like forms like SQL and stuff that is much easier to reason about. And Spark will continue, it will take that query and run it in an incremental fashion and continuously update the answer as new results, as new data comes in from, say, Kafka or whatever. So, to give a high-level overview of what a structured streaming query looks like, this is an anatomy of a streaming word count from Kafka writing out the counts back to Kafka. So the first step is to actually create a data frame from Kafka as a source. You specify the format as Kafka, the options of how to read, what topic you're going to subscribe from, and there are lots of built-in support for multiple different sources. Now that you have created a data frame, you can use usual data frame operations to transform the data, to aggregate, to calculate the counts. Then you can specify what you want to write out to, in this case, another Kafka topic. And then finally, you specify how to exactly process it. So let's say I want to process it using every 1 minute batches. And so you specify the trigger interval as 1 minute, and the output mode, which is essentially says that I want to write only the updated counts every time there is, in every 1 minute I want to write out only the updated counts. So we specify the update mode, and then we specify the checkpoint location. I'm going to talk in more detail about it later. The checkpoint location is a path to HDFS compatible file system, where the engine would write all the necessary information like offsets and other stuff that is necessary for the streaming query to recover from any failure. And finally, you start the query. And when you start the query, what happens is that it takes this streaming query that you have set up using the DataFrame API and converts internally into a logical plan, which is a very high-level logical explanation, representation of the exact computation you want to do. Then Spark SQL's planner comes in and takes the logical plan and converts into a very optimized physical plan, where all the optimizations that we have done into the Spark SQL engine from in the last 2-3 years really produces a very optimized plan. And from that single plan, since the Spark planner is aware that this is a streaming query, it generates a continuous series of incremental plans, which is designed to take just the new data from Kafka and write it out, the updated counts, back to Kafka. So this is what Spark SQL does. It takes your query, and which is a very batch-like SQL-ish query, and automatically converts it to a series of incremental execution plans that run continuously on your cluster to continuously process data from the input stream. Now, what happens behind the covers is that if you're running actual aggregates, like these are partial, you need to remember the partial counts for every word across these executions. And that is done by keeping track of what we call a distributed state. so the partial counts are kept around in the executor's memory as distributed state, and every incremental execution reads the previous version of this distributed state. The partial counts updates them to create the next version of the distributed state. And all these changes to this state are backed by writing a write-ahead log of all the updates into the checkpoint location that you have provided into HDFS S3 or something like that. In all, the engine knows exactly how to recover from these versioned distributed state, and therefore it gives end-to-end exactly one's fault tolerance guarantees for both stateless as well as stateful stream processing. And what this talk is about is that this talk will essentially go deeper into exploring what these stateful operations look like, how to use them, how to use watermarks on them to limit the amount of state, how to write your own custom arbitrary stateful processing, and how to monitor these stateful queries so that it doesn't blow up your memory or if it's running slow and stuff like that. So again, there are lots of things that I'm going to assume and that I won't cover in this talk. Please take a look at my previous talk. So first step is streaming aggregation, which you already got a very brief look. So you can aggregate not by key, which is like simple word count, but you can also aggregate by windows on event time. And here, all you need to specify is what is the time column in the data frame on which you're applying windows, and what is the duration of the window. It can be non-overlapping windows, like in this case, 10 minutes, or it can be overlapping windows where you say that I want windows every hour moving every 30 minutes. So these are overlapping windows, and the system takes care of actually figuring out for every record which one or more windows does it fall into, and accordingly calculate and update the counts or average and stuff. You can also combine both non-window as well as window grouping keys together, and you can also combine multiple aggregations to be computed at the same time. For example, in this last query, I'm actually computing averages and correlation on the value both together, and the system takes care of figuring out how do you compute all of them together. And of course, you can specify your own custom aggregations as well through UDF interfaces that we provide. So now, the interesting thing is that for windowed aggregation, this mechanism automatically takes care of late data. Because if you think about how grouping by window works, you can have multiple windows open. So suppose if you're windowing by 1 hour windows, then you can, in the state, you keep around multiple 1 hour windows, and if a data point that is 2 hours old comes in, it just gets added to an older window, an older grouping bucket, and its count appropriately updated. As you can see in the slide, the ones that are marked in red are essentially older windows, not the latest window, but still gets updated as late data comes in. But the problem with this approach is that the system does not really know when it can throw out a window from the state. So the state will keep growing indefinitely. So, and which is not good for any practical production system, because you don't want the state to grow indefinitely and keep adding more and more resources to the cluster. So we need to tell the engine that your state, that your data can be at max late by 3 hours, let's say, and so any windows older than 3 hours is not going to get any further updates, and so you can throw them out. And that's what we do using watermarking. So watermark is defined as this moving threshold that trails behind the maximum event time the system has seen. So let's say the Spark SQL engine at this point of time has seen that in all its input data, the max event time is 12:30. And we have specified that, the trailing gap is 10 minutes. So that means the watermark is currently at 12:20. And as the max event time keeps moving forward, as it gets new data, the watermark also keeps moving forward in that way. Now, what is the significance of this trailing gap, which we will call watermark delay? It determines when data is actually late, whether to consider it or not. So data may be less than 10 minutes late in this case, we will allow it to be aggregated to an older window. But if data is actually very late, it's too late, that is more than 10 minutes, that is, it is older than what the current watermark is, then we will not let the data to be aggregated. And this is to ensure that any windows that are older than 10 minutes can get cleared off from the state, and therefore we essentially drop all data that is older than the watermark, because the corresponding state and the partial aggregates has already been dropped as well. So, and the way to specify this in code is simply you specify with watermark, and in which you specify the timestamp column in your data frame, and this watermark delay, which in this case was 10 minutes. And that's it. And the system, when it's running aggregation, will automatically figure out how to use this watermark value. Now, it's important to note that this watermark, even if you specify in your data frame transformations, is really useful only in stateful streaming queries. So if you don't have any stateful query, in any stateful operation on your data frames in your query, this watermark will just be silently ignored, because it doesn't need to use the watermark at all, because it's not keeping any state. And also, since all of these data frame operations can be run both on batch and streaming with exactly the same semantics, this watermark makes absolutely no sense in a batch query. So again, in batch queries, this watermark will be just ignored. So now, underneath what the engine does is basically, if you notice this graph, the x-axis is the processing time, which is the real wall clock time, and the y-axis is the event time in the data itself. As it receives events at different points in the event time, the system automatically tracks what is the max event time the engine has seen, and accordingly, based on the watermark delay, calculates what the watermark should be, and keeps continuously updating it. And then when there is data that is late, but still still newer than the watermark, that will be allowed to aggregate. If it's not newer than the watermark, then it will be dropped. We have written a blog post to explain this in more detail. Please take a look at our blog post. Now, the important thing to understand here is that now you have the power to trade off between how much state you want to keep and how much lateness you want to consider in your application. So if your application is such that you want to consider very late data for eventual correctness, then you have to configure your cluster to keep more, to have more memory so that you can keep around so much state. And vice versa, if you don't care about late data because there's no point taking important decisions on late data, the point is moot, then you don't need to keep around that much state. So this is a trade-off that you can do by specifying the watermark, and this is true not just for streaming aggregation, but for any stateful operation that I'm going to talk about in this talk. So that brings it to the next stateful operation, which is the streaming deduplication. And this is something we support out of the box. You can just specify that here is a data frame which contains a stream of data that may have duplicates, and I want to drop the duplicates that have the same unique record ID. And the system takes care of actually figuring out, of keeping track of all the past unique record IDs as state, so that any new data that comes in, it can check against the old unique records that it has seen, and if it has already seen that record, it will just drop that record and only let unique records pass through. Now again, the same problem happens, that how long can a unique record, can duplicate records arrive, and that will determine how much state you have to keep. And for that, you can also apply watermarks out here, but you have to be, what you have to do is that not just apply watermarks, but you also have to include the timestamp in the data, the event time, as part of the unique column as well. So that essentially means that a duplicate record will have the same record ID as well as the same timestamp, which that's the assumption we go by. And you have to be aware that the timestamp should be the same in duplicate records. For example, if the timestamp was generated by, let's say, the IoT device, and then duplicate record generated by the IoT device is likely to have the same timestamp. However, if you're using timestamp based on using the timestamp in Kafka, for example, when the record was ingested into Kafka, then it may so happen that the two duplicate records can have different timestamps, and in which case the system will consider them as two different records, not duplicates. So that is something you have to be aware of while you're using this watermark and the timestamp as an additional unique column. But with this, you can limit the amount of state you want to keep and consider how long to keep the watermark around, how old data to keep around for deduplicating. The next operation is something that we have been working on over the last 1 month, and I'm very, very excited about this because this is something that has been in demand for over a year, and we're finally doing this, and that is stream joins. So about joins with streaming data, Spark 2.0 right out of the box supported joining streams with static data. And that has already been there since the beginning. What we are adding in 2.3, which is the next release, whenever that is going to be released, will support joining between multiple streams of data. And to understand this, let's start with a very canonical example of ad monetization. So you have a stream of ad impressions coming in, which says when an ad was displayed, and a completely different stream of ad user clicks coming in, which essentially says that this ad was clicked. And essentially, you want to join them together to match impression with a click so that you can monetize those clicks. So here, to do this sort of joining together between two streams, what you have to do is that you have to keep around past events as state. Because it may so happen that your impression came in much before the corresponding click, or even vice versa. The click got somehow delayed and the impression came in, the click got delayed, impression came in later, or impression got delayed, which came after the click. So to do a proper correct join, you have to buffer past events, both on the impression side as well as on the click side, because a match on each side can come at any point of time in the future. So that means that you have to keep around all this data from both the streams as state on both sides of the join. Now, but the system automatically takes care of actually doing all of this. So all you need to do is just simply do a simple join. For example, we support inner join where you just specify the two data frames and the equi-join condition. Same add ID on both click and impression. But the interesting thing to note is that since here we cannot reason about in the query that if I receive an impression, how late can the click come? The click can come at any point in the future if we do not define any additional constraints. So that means that we have to buffer everything to ensure correctness, that we never miss a match between an impression and a click. So to avoid this, again, we have watermarking to the rescue, but actually it needs a little bit more. It needs more additional time constraints by which the engine can reason about that this impression cannot possibly receive a click that matches with it anymore, and vice versa, that a click, here is a click that cannot match with the impression anymore. So we can discard them. And to provide these time constraints, what we support is the following. So let's make the application much more realistic. Let's say that impressions can be at most 2 hours late in the pipeline over the internet and stuff. And based on that, we define a watermark on the impression stream that impressions can be, the watermark delay to consider is 2 hours. Similarly, clicks can be at most 3 hours late, and we define another watermark on the click stream as well. Then, and here is the most interesting thing. Suppose we can we can define a constraint that a click can be generated at max 1 hour after the corresponding impression. So that means that we can write a condition, a range condition, that not only the click ID, the add ID of the click and the add ID of the impression needs to match, but the time of the click must be between the impression time and impression time plus 1 hour. And so using this range condition, we are constricting of what click can match with what impression with respect to time. Now, with these constraints, what the Spark engine can calculate is that an impression needs to be buffered for at most 4 hours. And I don't know exactly how to exactly do the math on a PowerPoint presentation, but if you do the math, and well, actually you don't need to do the math because the Spark engine does the math, but essentially a 3-hour late click may match with any impression that may be 4 hours old, that is with that 1 hour time frame and stuff. So anyways, doing this math, the engine figures out that you need to keep last 4 hours of impressions and last 2 hours of clicks to do a correct match between data that was late within those watermark constraints. And any event, clicks, or impressions that is older than that gets cleared off by the engine. So this is something that happens automatically. And the same thing happens with outer joins as well, except in inner join, this time constraint is optional because the inner join can, given with the time constraint, the inner join can provide correct results by providing only the matches. For outer join, this time constraint is not optional. You have to specify it because for outer join, remember the semantics of outer join, if something that doesn't match, for example, the left outer join, if there is no match on the right side, you need to output nulls on the left side. So to argue whether we can output null or not, we need to know that on the left side, it will not match with anything on the right side at all ever. So now we can output it as nulls. So to enforce that, we need the time condition, the time constraints, and therefore for outer joins, you have to specify the watermark and the time range conditions. And to do left outer join, right outer, all you need to do is specify the join type in the DataFrame join operation. That's it. So this is going to, we just added this. It's in Spark Master. If you are really excited about it, you can try out. But it'll be available generally in Spark 2.3, which probably around December, January, can't make promises, usual Apache process. So the final one, and this is the other most exciting thing and the most generic, the coolest and the most complex thing in structured streaming, but also the most powerful thing in structured streaming is being able to do arbitrary stateful operations. So many use cases don't quite fit into the standard SQL semantics like SQL operations. For example, if you are a service provider, much like Databricks, you want to track your user activity to see when the user is online, when it's inactive, when it has logged off, etc. And so here is a specific example. So let's say we want to monitor input user actions and output the latest user status on what is the current status of the user. To do this sort of a thing, we have added in Spark 2.2 two operations called mapGroupsWithState and a more flexible version of that called FlatMapGroupsWithState. These are general APIs for essentially keeping per key user-defined state. And for those who have used these streams, this is much more powerful and efficient than map-with-state or update-state by key. So you guys should consider upgrading to this. And this is only for Scala and Java. So let's take a look at how to use mapGroupsWithState. So the first step is to define the data structures that will define what the input is, what the intermediate state that you're maintaining is, and what the output is. In this case, we have defined user action as the user's action, and the intermediate state as user status, and the output event is also user status. And it could be anything, it could be different as well, but in this example, let's roll with that. So once we have defined the data structure, you need to define a function that takes as input 3 different things. One is the user ID on which you are grouping by, a bunch of new actions that particular user has done, that's an iterator of user actions, and the previous state or the previous status of that user. And that is through this thing called group state. And given these input, your job is to essentially write your custom state updating logic, which which is essentially can be broken down into these 4 parts. 1, you need to get the previous user status. 2, you need to process the new actions of that user to update the user status. 3, you need to explicitly set the updated user status back as state, that you need to explicitly update the state. And 4, finally, return that latest updated user status. So now, once you have defined this state updating function, you can apply it on your stream of user actions by first grouping it by the user ID and then calling mapGroupsWithState with this function. And then the engine will take care of actually calling this function for every group whenever there is new data for that group, etc. The cool thing is that this operation works on static batch data frames as well. So what you can do is basically write this function, and then instead of testing it on a stream of data, you can actually test it on a bunch of older past user actions. And you can apply different sort of tests on it, etc., to test the correctness of your logic. Now, if you have written your update function in such a way that it is robust against late data handling and stuff, then you should get the exact same results if you process a bunch of past data as a single static batch data frame, or treat it like a streaming data as well. You should get the exact same results. And this gives you a very powerful primitive to do any sort of arbitrary stateful processing that you want. You can implement streaming joins on top of this. It won't be as efficient as our streaming joins, but you still can. You can implement any stateful operations using this. The other very cool thing that we support out of the box is timeouts. Basically, for example, if your user is not doing anything for a long time because he shut down his laptop or in flight, then you have not received any data for an hour, you want to mark that user as inactive. And for that, you need timeouts. And the way we have defined timeouts is that whenever you hit a timeout, and I'll explain how we hit a timeout, then we essentially call your function once again, except with an empty iterator, because there are no new actions, you just call that function. Now, inside that function, you can do whatever bookkeeping that you want to mark the user inactive and stuff. So there are 2 kinds of timeouts, essentially, the default being no timeout. Timeout is disabled by default. You have event time timeout, where it's based on if there is no data for a while tracked by event time, or there is processing time timeout. Let's actually walk through how to use event time timeout. So the idea is that first you set the timeout configurations event time, and then you have to enable watermarking. And I'll explain why. So also you need to modify your state updating function to explicitly set the timestamp when you want to timeout. So in this case, for example, you probably would want to track the max timestamp seen in that particular user's actions, and then set a 1-hour timeout from that. So that's how you explicitly set the timeout timestamp. And then also, when timeout indeed happens, what do you do? In this case, you want to update the user status to handle timeout, and maybe you just want to remove that state because you don't want to track that user anymore at all. So you specify that. And the way it works is that, so if you remember Watermark, it is calculated based on the timestamp across all the groups, across all the users, across all the data for all the users. So if a particular group does not receive data for a while, the watermark will still keep growing based on the other users' data. And if there is no new action for that user before the watermark hits the timestamp that you have set, then that function will be called with an empty iterator, and also there's something called has timed out that will be set to true. But if there is a new action before watermark reaches that timestamp, then the function will obviously be called with new action data, and the timeout will be disabled automatically. So every time that function is called, you need to explicitly set the timeout timestamp and can enable it explicitly. Processing timeout is very similar, except it doesn't use watermark or event time at all. It essentially uses the wall clock time of the server on which you're running. And it is much simpler, but the idea is very similar. Instead of setting the timestamp, you actually just set the timeout duration. And this is completely independent of watermarks. So it's simpler, but on the flip side, it is less robust. Because, for example, if your streaming query is down for a while because of some cluster outage and stuff like that, then once the query comes, you restart the query, the processing time has actually moved forward. So there is likely to be a whole bunch of timeouts right out of the box. But in some cases, processing time is useful, especially when there isn't a very clear event time in the data itself. The last but not the least, there is a more generic version of MapGroupsWithState called FlatMapGroupsWithState, where the key difference is that in MapGroupsWithState, you have to return only one record from that function for every group. In this case, you can return any number of records, including no records at all. And this may so happen that you don't want to return the status, but a very specific number of special actions, which there may be no special actions at some point of time or a bunch of special actions. So in this case, you just return an iterator containing those. But the other important thing to remember in FlatMapGroupsWithState, because it's much more flexible, it is really kind of opaque to the Spark planner to what these outputs are. And for that matter, we have added this thing called function output mode, which kind of gives more insights into what these outputs are. It could be that these outputs are essentially key value pairs, in which case every successive output is essentially updating the value of a particular key. Some of the columns may be the key in the data. Or these outputs may be completely independent rows that are essentially being appended to the same result, to the result table. But now you have to specify what these outputs are. And this function output mode essentially allows the Spark planner to reason about how to compose MapGroupsWithState and FlatMapGroupsWithState with other operations downstream. And because the semantics are different, if it's key value pair versus independent rows. Anyways, I'm out of time, so I'm going to rush through this couple of slides. So to monitor streaming queries, there's something called the running streaming query.lastProgress, which gives you a whole lot of information like input rates and processing rates, but it also gives the memory consumption of the state and how many records are present in the state, etc. You can also get it continuously in an asynchronous fashion using the streaming query listener API. You have to implement your own listener, and it'll get callbacks. And if you want to dig deeper into a particular operation, like an aggregation or something, and you want to know that why is your aggregation running slow, is the writing to HDFS taking too much time, or something like that, then you can always go to the Spark UI in the SQL tab and take a look at the DAG of SQL operations, and it'll give more information about more specific state metrics that is specific to that particular operation. Anyways, we have been writing a lot about these operations in our blog post. We'll continue to write about this. I'm aching to write a streaming join blog post soon, so please stay tuned and keep following our blog posts. Anyways, that's it for today. Please try Spark on our platform. And we have gone to great lengths to optimize structured streaming on our platform. Thank you very much.
I look forward to that blog post. Awesome talk, TD. Thank you so much. That's hot off the press. You just can't get any more of like the most up-to-date information anywhere else. So with that, I'm sure there's going to be a couple questions. Yeah, go ahead and kick it off.
Thanks for the great talk. Very helpful to know about this. So immediate question about the memory guarantee. So as soon as the state is kept, so how can I make sure that it will not blow up? Basically, it will not go Stack Overflow.
Well, that's why you need to monitor the state continuously. And in Databricks, we have made it very easy by exposing the size of the state, etc., in our notebooks interface itself. But if you're writing outside, yeah, you have to explicitly monitor, etc. Because at the semantic query level, the engine, we cannot provide any guarantee on what your data quality is, like how many different values your data can have and stuff. So we will do a best effort attempt to compute the correct results, and if that requires keeping more memory, then that is something you have to provide. So the best way to do is explicitly monitor your streaming query.
Okay, fair enough. Thanks a lot.
Yeah, in that progress or status part of the JSON blob that's returned when you asked for it, there's something, I think it's like aggregation keys or something like that.
Stateful operator info or something like that.
Yeah, and inside of there it'll say how many keys it currently has, and then that's basically you can try and scale out.
That's basically.
Yeah. Cool.
Hey.
Russ.
Yeah, I was just wondering, kind of on the same line, is there anything where it would just tell us what the full buffer size is in terms of hours or minutes? And can the query engine warn us in advance if we've specified boundaries that essentially eliminate any possibility of a join occurring? So imagine that you watermarked data in such a way that the join would never be possible, or that there's always 0 records.
Right now, there isn't a way to kind of give that sort of warning because it's really hard for an engine to know what your actual intentions are. So the only interface to your actual intentions is the DataFrame operations you call and the parameters. So it's really hard for us to reason about what cannot possibly match and stuff like that.
Some like AI analysis exception is what you're looking for. Really quick question.
Quick question, yeah. So in terms of like error handling, sometimes I need to retry a stream message, and how would that supported in this? Because you mentioned about deduping. Is there a manual way to disable that and replay a message and process it?
So wait, what sort of error handling are you talking about?
Just in case I need to retry or reparse, reprocess a message, is that possible?
That is definitely possible. There's nothing to do with stateful.
Okay.
Actually, for example, if let's say you get a corrupted record and because your query fails at that point of time, what you can very easily do is add an additional filter in the query, which will find out corrupted records and drop it elsewhere. And you can restart the query exactly at the same point where you left off, and it'll start off exactly where it left off.
And that's all that we have. You can just come up and bother him and stay around.
And you can see Bill is showing me up the
Yeah,
stage.
there we go. Let's give him another hand.
Thank you, Bill. Thank you very much. You have been a wonderful audience.